Hello and welcome to lecture 6 of our plasma physics course. Today we're going to talk a little bit more about drifts. We've been talking about drifts for a while, but we'll also take a little bit of a break to talk about something else. If you remember, or if you just watched lecture 5, the last thing we discussed was the so-called curvature drift. And it's called the curvature drift for a good reason. It does happen only if the magnetic field is not straight. And we wrote the expression for the curvature drift in a couple of different ways. Let me remind you that the drift velocity is going to be equal to the mass of the particles times the square of its parallel velocity divided by the charge. So notice that the charge with sign appears in this expression. That means that the drift is in opposite directions for differently charged particles. And then you have the curvature radius divided by the curvature radius square, crossed with the magnetic field divided by the absolute value or the norm of the magnetic field square, which you can also write as mass V parallel square over Q. And this part doesn't change, but replacing the definition of the radius of curvature, we can write this as B cross B hat dot grad B hat, where B hat is the unit vector aligned with the magnetic field divided by B square. What am I doing? And now I'm going to pause here for a moment because I need to make a little aesthetic change in the video. Just hang in there. Okay, here we are back. The beauty about recording the lecture is I can actually pause it. You didn't have to hang in there very long. And you'll notice what we've changed. One is that the screen is not white anymore. And the reason why I did that is that somebody mentioned to me that the white background is really hard on the eyes. I hadn't realized, but yeah, that kind of makes sense. And so I changed it to this, whatever you'd call it, color. For the people taking the course, if this color bothers you, just let me know and we'll change it again. We'll look for a good color. Unfortunately, I forgot that I have to change it every time I open a new page, and slipped my mind. Somehow it doesn't stick with the app. And I also added some lines so that I don't quite do this kind of thing where my lines are not straight. Well, I'll still do it, but maybe I'll do a little better. Let's see how it goes. Back to our drifts. I'm going to look now at vacuum fields and make a little bit of algebra. It's going to be pretty straightforward, and we'll see how to combine the grad B and curvature drifts. They are actually related because of Maxwell's equation. You'll see in a moment. We're going to take a particular case, the simplest case. I'm going to assume that J is equal to 0 that is, there is no current density. That's why, let's give myself a little more space. Here you go. That's why I'm calling this vacuum field case. Okay, let's see what the geometry looks like. Maybe I can use a different color to make my drawing here. We have some magnetic field. Here's my radius. And here I have a little arc. There's no way I can make it do as pretty as I would like. So I'll just do some hand drawing. This is going to be the direction, the theta direction. Let me use E sub theta as unit vector. And of course, the radial direction is going to be E sub r, the direction of the radial coordinate. Working in polar coordinates, in local polar coordinates. And the magnetic field is in that curved direction. This B is in this direction. And this distance, of course, is r. That's going to be equal to our radius of curvature. I'm going to look at a static case, and therefore del cross B is 0. Then I can take the radial component of the curl of B, which is 0, and see what it looks like. Now, by construction, notice here that B sub r is equal to 0, and also B sub z is equal to 0. In other words, B is equal to B theta E theta hat. All we have is theta component of the magnetic field. Then del cross B is 0. Let's see what the radial component looks like. I'm not going to do the algebra, you know how to do this. But all we have left, since the oops, sorry, misspoke. I need the z component. Since the radial component of the field is 0, all that appears is the term that involves the theta component of the field, and that's going to be 1 over r d over dr of rb theta. As usual, check the NRL formulary if you are confused about the coordinates and how to write differential operators in this case, polar coordinates. And this I can expand to db theta dr plus b theta over r. Remember, this is equal to 0. And therefore, this pretty much says that db theta dr is equal to minus b theta, I'm taking this to the other side, over the radius of curvature. Which I can write as grad B R component is equal to minus B over RC, which is where I wanted to get. As a reminder, check the NRL formulary for differential operators. Almost. In polar coordinates, curvilinear coordinates in general. Let me call it curvilinear. Okay. Well, so what did we actually obtain? Well, the magnetic field is in the theta direction. Therefore, the piece we just calculated, grad B in the R direction, is perpendicular to the magnetic field. And in general, the direction perpendicular to the magnetic field is going to have components in both R and Z. There's going to be something like alpha E sub R hat plus beta E sub Z hat. Whatever alpha and beta are, make it a unit vector if you like. It doesn't matter. I'm just worrying about the direction. However, with the assumptions we're making, grad B in the Z direction is 0. In fact, you can see this by taking del cross B and taking the theta direction. This will give you dB theta dz, which needs to be 0, which is the same as saying that the Z component of the gradient of beta or the gradient of B is 0. Okay, great. In conclusion, the perpendicular, if you prefer, can use the symbol, perpendicular component of grad B is equal to minus B R sub C over RC squared. R sub C is the curvature radius, which is in the radial direction. That's the direction of my gradient. The value I just wrote up there was absolute value was B over sub R sub C. So these two are the same. These two expressions are the same. Okay. What then? The grad B drift is written as no. Oh, getting this too. I don't know that there is any way to actually keep a lowercase in there, so I'll have to deal with the automatic capital letter. All right, it's not a big deal. We're going to have V grad B, sub grad B which is the same as V sub D. That's another notation that may occur. I'm going to write it as a vector. That's going to be equal to remember, M V perp squared divided by Q. B cross grad B over B to the third power, since I'm using the full B top. And let me make this a straight line. Better. Equal MV perp square over 2Q RC cross B divided by RC square B square. And the total drift in this vacuum field, where I'm also assuming that the electric field is 0, is going to be given by the grad B drift plus the curvature drift. So it's going to be V grad B plus V R let me write them in the opposite order. It's just going to be prettier. So let's make it V sub R plus V grad B. So this is the curvature. Again. Plus the grad B drift. All right, what does it look like? Let me write it down here. That's going to be equal to 1 over Q MV parallel square plus 1/2 of MV perp square. And these two are in the same direction. RC cross B divided by RC square B, B square. Well, there is a bunch of things to note here. And let's see what they are. Well, the first one is that the two drifts are in the same direction. The second one is that they are in opposite directions for ions and electrons, for, let's say, for opposite charges. And you also see that there we have pieces that look like mv squared divided by 2 or something like that. They're combined in some strange way, but you see that there is something that looks like energy in the brackets. So that's interesting. They're my drifts velocities are proportional to particle energies. And I want to be careful here, but let me make the statement. And then I'll clarify what I mean. The curvature drift is proportional to what I'm going to call the parallel energy, while the grad B is proportional to what I'm going to call the perpendicular energy. Don't get upset. I'll clarify this in a moment. Oh. Thanks. Perpendicular energy. Now, we, of course, very well know that energy is a scalar. There is no such thing as the parallel energy or the perpendicular energy. What I mean by those expressions is a little of a shorthand to say this is the energy associated with the parallel velocity of the magnetic field of the particle with respect to the magnetic field, or the perpendicular velocity of the particle with respect to the magnetic field. But as we all know, and as we're not going to forget, energy is a scalar, so there is no such thing as a parallel component or a perpendicular component. What I mean is the energy that you obtain from squaring the parallel or perpendicular velocity. And if you actually look at this expression, you'll notice that this actually multiplied by 2. Okay. Is there anything else? Well, yes. Here it is. Let me take the average of the kinetic energy calculated using the parallel velocity. Well, this is going to be T over 2 for a thermal distribution of particles, and the same for the average of the kinetic energy calculated using the perpendicular velocity. Now, be careful with this part. You've all taken statistical mechanics. This is going to be T and not 2T. Sorry, not T over 2. So it's going to be double that. Come on. Hello? Having technical problems. All right, let me pause this for a moment and let me try to fix the issue here. Okay, not quite in the way I intended, but it did work. So let me specify here what was missing, what I forgot to write. Oh, it's not a rheumatoid, come on. It's a thermal distribution. Okay, so that's what happens. And the reason why this happens is that I don't have to convince you, I'm pretty sure, is that we have 2 degrees of freedom in the parallel direction. And where that takes us is the following, that the sum of the curvature plus the grad B drifts for a thermal distribution of particles is going to look something like this. It's going to be 2T divided by Q times RC cross B divided by RC square B square times no, wait, it's times nothing. I got everything. This is also equal to 2T over Q B cross B dot grad B with the proper hats divided by B square. Which is where I wanted to get. Just wanted to show you that for a thermal distribution of particles, you end up with an average drift that depends on the temperature, that is, depends on the kinetic energy of the particles. All right, so that was a little more information about drifts. But if you remember, that wasn't that long ago, I promised that there would be a bit of a break. I'm going to follow the notes I'm following also in the naming convention. So I'm going to call this an interlude. And this is going to be about the toroidal confinement of single particles. Sorry about that. Thank you. The reason why this is appropriate here will hopefully become clear pretty quickly. Let me also make, no, I want to scribble, go away. A bit of a division here. Now, this is going to be challenging because I have to do a bit of a plot, but let's see. Let's cheat a little bit. And let's say that we have a toroidal component of the field that's in this way, in this direction, I'm sorry. So this angle is going to be the angle phi. I'm going to show it in a second. So this, I'll make this an arrow. This, by the way, is a circle. The idea here is that we're looking at it from above, from a certain angle, and that's why it looks like an ellipse. So this angle is phi. Lowercase. And that's the toroidal angle. This is my coordinate r. This is vector r. And then here in a plane perpendicular to the toroidal direction, I'm going to have, let me maybe make it in green. It's never going to work. That's not too bad. This is going to be the lowercase r direction. And this is going to be my angle theta. Which is, of course, just as a reminder, the poloidal direction. Okay. Why on earth did I spend my time doing this thing? Well, what happens with the curvature in B drifts and grad B drifts? Let's see. Where we can use the results we got for a vacuum field, because I'm looking at a single particle. I have my vacuum toroidal field and whatever else. Let's just say there is just the toroidal field. That's the only component I have. And I want to calculate the drifts, if any, for a single particle that I'm trying to confine. So as usual, I'm going to neglect the current that's carried by my single particle and therefore my magnetic field is given is the vacuum field. I'm not going to touch it. Well, we just wrote this. The drift velocity is going to be 1 over q mv parallel square plus 1/2 mv per square times r, big R, that's the radius of curvature, cross b divided by r squared b squared. And it immediately follows that the magnitude of the drift velocity is 1 over q mv parallel square plus 1/2 mv perp square times 1 over b times r. I'm just taking the absolute value of the expression above. Okay, what's the direction? Well, I do the cross product between the r and phi components. Should be clear. I hope it is. That the drift velocity is in this direction. Could be plus or minus. I'll leave in the charge in front. And if you work it out, the charge appears that way. That means that ions drift up and electrons drift down. By ions, I mean, of course, positive ions. Okay. So is that a problem? Well, clearly that's a problem. My ions are, if I want to confine a single ion this way, I'm not confining it because it's just going to move upwards and get out of my magnetic field. If instead I want to confine an electron, well, it's just going to move down and get out of my magnetic field. Are things going to change if I have a collection of particles? Well, yes, they're going to get worse. And let's see how. Let's see if I can make a reasonable approximation of a circle here. Let me make sure that I clarify. What I mean here. Okay. So let's say I have this circle here. Now, this green circle is the same green circle as I had above here. That is in the poloidal plane. That is a plane perpendicular to the toroidal direction. Let's see. Maybe this will make it more clear. Those are R and Z. Now, let's see. Okay, very good. I had to pause this for a minute to get another circle to appear where I wanted it, and we got it. So let me tell you what happens now. what happens is that ions are going to move up and electrons are going to move down. And therefore, I'm going to have an electric field that points from the positive charges to the negative charges. That is this way. But remember, the toroidal field is amount of colors, and I'm going to make it this big color. This way. You see that the electric field and magnetic field are not parallel. And therefore, if I, for any reason, decided to take the cross product, I'm going to get a vector that's not zero. And that actually goes in this direction. And you remember what that does? An electric field and magnetic field that are not aligned are going to give me the E cross B drift. And that's in the radial direction. So my whole plasma is just going to get out of the way and be gone forever. So that's great. Well, let's see, what can we do, if anything? Well, one thing we can do is remind ourselves that we only use the purely toroidal component of the magnetic field. So it may be that things are not so bad if we have a more complicated geometry of the magnetic field. So if you've ever wondered, why do stellarators, why does CTH look like a pretzel designed by a cubist painter? Well, here's why. To avoid this problem. And let's see how we can work on a solution. I'm going to try a different field configuration. And I'm going to restrict this to a single type of particles just to make it more manageable, not have to worry about signs and so on. And we'll see that this works for both types of particles. So I'm going to start from a beam of electrons with zero perpendicular velocity. That is, all the velocity of the electrons is in the parallel direction, singular. V parallel not zero, V perp is zero, then I can write the drift velocity as mv parallel square over q times 1 over b, which is b toroidal, times r. And this is the absolute value of drift velocity. So that's a velocity in the vertical direction. So I could add z component of the field, and that's somehow going to fix things. Let's see how that works. If bz is not 0, I'm going to get a velocity v that is v parallel times bz divided by b toroidal. This is strictly I'm assuming that bz is much less than bt. The z component is much smaller than the toroidal component. And I'm going to leave it at that. I'll let you chew on it if you're not convinced. But yeah, this actually works. Therefore, let's say that I want Vz to be 0, and that's the idea. I don't want the drift anymore. Well, that's going to be equal to V parallel Bz over Bt. I prefer to use B5, but I am following the notes that I have that are not my private notes. And that's the other piece that I'm going to write this way. Long story short, if I have a z component of the field that's equal to minus mv parallel divided by rq, then the z component of the velocity is going to be equal to 0. And oh, oops, sorry. I don't know where this q came from. So this is 1. Okay, so that's how we can solve this problem. Is that the solution really the solution of our problem? I'll let you think about it for a second, pause the video, think about it for a second. If you don't see it, I'm going to tell you. Actually, obviously now, this doesn't work. And the reason why it doesn't work is that I can fix it if I have the right amount of vertical field, but the right amount of vertical field depends on the parallel velocity of the particle and on the charge of the particle. That means I can make it work for only one particle. or one type of particle. If I have a bunch of identical particles, all moving, I started with a beam, all moving with the same parallel velocity, well, this is going to work. And what if I also want particles of the opposite sign? Well, I need to change the sign of BZ. It's not going to work. So that's not the solution. Is that the end of the story? Of course not. We know that we can't confine plasma. Indeed, there is a solution. And that solution, sorry about that, is what's called the rotational transform. Let's see how that works. What I'm going to do is, instead of having a vertical component of the field, let me move back to my picture up here. I'm going to have a poloidal component of the field in the theta direction. So that's, B theta. Then what happens to the field lines? They're not circular as I had up here in the blue direction, with the red arrow. They're actually going to be helical. They're going to wind around the torus. And I'm not going to try to draw that. So if I look at the circle in the poloidal plane, I'm going to see a magnetic field that every time it goes around the torus in the toroidal direction once, comes back to a different poloidal direction in general. And in that plane, my field is going over an infinite number of revolutions in the toroidal direction, going to trace a circle, the green circle up there. Now, the equation of motion of a particle that's following the field is going to look like, let me type it. Not the equation, of course. Gonna draw the line somewhere. Let me be clear. This is the direction of the field. And the equation of motion is going to be r d theta dt is going to be equal to b theta over b toroidal. Now let me call it b phi. V phi, or since b phi is V phi is the part of the parallel velocity that is aligned with the toroidal field, I can also write this as b theta b phi times b phi over b total b times v parallel, or b theta over b times v parallel. Now let's see if I can, so that will be the equation of motion for the trajectory for a particle that's following the field. Now let me add the drift. What I'm going to have is r d theta dt is going to be equal to the piece I just wrote, b theta over b times v parallel plus v drift times the cosine of theta, because of where I am in the direction of the relative direction of theta and z is going to depend on where I am in the cross section. So here is the radial direction. That's also going to be the direction dr d theta. I'm sorry, dr dt. How much the direction of the velocity that's radial, so how much the radius over which the particle is moving is changing over time. Then I have this direction. Let's do it in a different way. I hope this helps, having different colors. So here I'm writing velocities. Dr dt is the radial velocity. R d theta dt is the polar velocity. And last but not least, v drift is the drift velocity. And of course, this is the angle theta. So you see that there is an angle between r d theta dt and v drift. If theta is equal to 0, they're parallel. If theta is 90 degrees, they're perpendicular. So the component of the v drift that is aligned with the r d theta dt that I'm writing is going to be proportional to the cosine of theta. I can see that. Also, the other piece, the dr dt that I've not thought of, now that I see, well, that's going to depend on v drift also. So r d without r, the radial velocity dr dt is just going to be given by v drift. So that's the only piece I have, multiplied, of course, by the sine of theta. So this is 0 when theta is 0. It's equal to v drift when theta is 90 degrees. And I got these two equations together. So I can take the ratio of the two equations. So I'm actually dividing the second one by the first one. I'm trying to get rid of the dt. I'm obviously treating the differentials as finite quantities. I'm assuming I can simplify them, treating derivatives as fractions. Depending on which math course you've taken when you were in undergrad or graduate school, this may be shocking, or yeah, I know I know exactly what's happening, but I promise you it's legitimate and the result is going to be correct. So the last step I'm going to do, and then we'll finish this calculation in the next lecture, is take the ratio of those two, and I'm going to find that 1 over r d theta is going to be equal to v drift sine of theta divided by b theta over b v parallel plus v drift cosine of theta. And we'll see where that takes us in the next lecture. So I'm going to leave us with this, where we still got something that's dependent on v parallel, so we're not done, but let's see where this takes us. And thank you for listening to this lecture. I will see you next time.